Hey guys, now we're going to do part 2 of Unit 4, Lesson 5. We're going to learn how to write empirical formulas and molecular formulas. So an empirical formula is just some chemical formula that is the most reduced that it can possibly be. So NO2, for example. N2O4 is not the most reduced that it can be because both of these could be divided by 2 and they could still have a whole number, right? So the empirical formula is like the most reduced ratio between them, N1O2, right? The chemical or the molecular formula, it's also called chemical in this lesson, chemical formula, is the actual formula that it really is, and it will be a multiple of its empirical base formula. It might be NO2 times 1, or NO2 times 2, or NO2 times 100. So right now you can see it's NO2 times 2 because it's like everything got multiplied by 2. 1 times 2 is 2 and 2 times 2 is 4. So this is multiplied by a factor of 2 in this situation. So the molecular formula will always be some multiple of the empirical formula where you multiply the subscripts by a certain whole number. And we're going to learn how to identify the empirical formula. Here are the steps here, but rather than like reading them all out, I'm just going to practice with you on it. So this is how you find the empirical formula, and this is how you find the chemical formula. It's actually not that bad. So we're just going to go through it together. Let's look at this problem, which is one of the first, I think it is the first problem of it on your lesson. So find this problem in your lesson, and we'll do it together. So we're going to assume we have 100 grams. So it says the compound has this percentage of Na, this percentage of O, and that percentage of H, right? Well, if you have 100 grams, then 57.48 of them would be sodium or Na. So basically, you're going to convert those percentages to grams. So write down with me, please. It would help you, I think, if you followed along this way. So convert these, just literally write them down again, but put grams instead of percent. Just like this. Okay, and now we're going to convert them to moles. And the way that you convert is you always multiply, you do a fraction line, and you put what you're trying to convert to on top. We're trying to convert to moles. You put the unit that you want to cancel out on bottom so that it is opposite of the other unit, so that these grams and these grams cancel. Because the 57.48 is really over the number 1. It's on top, if you want to write that down like that. Now we need to put in the relationship. How do we know how many grams are in a mole for Na? Like, do we know that relationship? Well, we do on the periodic table. So on the periodic table right here, sodium's molar mass is 22.990. You can zoom in on it if you want. 22.990. I'm going to round that to 23. Okay, so we know that 1 mole of Na weighs 23 grams. So I'm going to put the 23 on bottom, and the 1 on top. The 1 is going to go with the mole, okay, because 1 mole of Na equals 23 grams. And so you match it with the units. So the 1 always goes with the mole. And so now we're going to calculate that. So really, we're doing 57.48 times 1 divided by 23, okay? And I get about 2.5 moles, okay? It was like 2.499. I'm just going to round it to 2.5 moles, okay? Now we're going to do it for the oxygen. We're going to go back to our periodic table and find the molar mass of oxygen. Oxygen's molar mass right here is 15.999. I'm going to round that to 16. Okay, so that means that for every 1 mole of oxygen, it weighs 16 grams. And my grams will cancel like that. So again, the 16 came from the periodic table. We're going to do 40 divided by 16. And I get, again, 2.5 moles, but this is for the oxygen. That was for the Na. And now for the H. The molar mass of H, let's see if we can find it here. I'm really zoomed in. The molar mass of H is right here, 1.008. Let's just make that 1 because that's super close to 1, okay? So 1 mole of H for every 1 gram of H, which is again going to be 2.52 moles of H, okay? So now we've converted everything over to moles. It will not always be 2.5 and be like the same like that. They're just kind of making it a little bit easier for the first problem. So now we've done this step, and this step. Now, when you have your moles, you take your grams, convert to moles, divide by whichever one of these is the lowest. And so these are actually all the same. All of them are 2.5, right? So we have the 2.5 moles of, I'm going to abbreviate and write MOL of Na, 2.5 moles of O, and about 2.5 moles of H, right? Like it's about 2.5. So they're all the same. So our lowest mole amount, which one of these is the lowest? Well, they're all 2.5. You divide every single one by 2.5. So what do you think 2.5 divided by 2.5 is going to be? 1, right? These are all going to just be 1. That is your subscript for each element. So our formula is going to be Na1, O1, H1, because each of these have a subscript of 1. So that can just be smushed together to be NaOH, because when you have a subscript of 1, you do not have to write it all the way out like that. So that is how we found the empirical formula for NaOH. To find the chemical formula, this is actually a little bit easier. So first, you write down the molar mass that they gave you. So this is the molar mass of the molecular or the chemical formula, okay? Grams per mole. That's the chemical formula, okay? Now we need the molar mass of the empirical formula. The empirical that we just got, we need to write that down. The one that we just got was NaOH. We need the molar mass of this substance as well, and we're going to compare it. So we're going to just find them on the periodic table like before. So if you remember some of these already, hydrogen's molar mass is about 1. Sodium's molar mass is about 23. And H's molar mass is, oxygen's molar mass is about 16, okay? So I'm going to write all of that down, 23, 16, and 1. And we're going to add those up. So 23 plus 16 plus 1 is 40 grams per mole, okay? So remember, the molecular or chemical formula is some multiple of the empirical. If you notice, basically, we're going to compare 39 to 40, right? Those are basically the same thing. It's not even like, it would either be the same or 2 times bigger or 3 times bigger. One way to find out for sure is to divide the chemical formula by the empirical formula. So I'm going to say that again. You can divide the molar mass of the chemical formula by the molar mass of the empirical formula. And that's going to be about 1, right? 39.9971 divided by 40 is like about 1.9999, right? So this means that the chemical formula is whatever the empirical formula is multiplied by 1. So it's going to be the same. It's also going to be NaOH. So the chemical formula in this situation is also the same. So this is a little bit of an easier scenario to do. So here's our answers for both of them there. Let's try one more and it'll be a good practice for us. And it's also from your lesson. So again, we're going to write down all of those percentages, but write them down as grams. 5.93, 94.07 grams. And then we're going to convert them to moles. You put moles on top, moles of H, grams of H on bottom. And now we need to put in the relationship by looking up the molar mass of H. If you can remember what the molar mass of H was, it's actually just 1. And then looking ahead, remember the molar mass of oxygen is 16. So going back over here, 1 mole for every 1 gram. So that's going to be 5.93 moles of H. 94.07 grams of oxygen. We need to convert that to moles. So 1 mole of oxygen for every 16 grams. Remember, I just got that from the periodic table. So we're doing 94.07 divided by 16. And I'm getting 5.879, okay? So then once we have the moles, we divide each of them by whichever one is the lowest. 5.879 is lower, 5.879. So we divide both of them by 5.879. So 5.93 divided by 5.879, that's about 1 again, okay? And then for this one, it is 1, 5.879 divided by 5.879. So again, this tells us the subscripts. Our formula here must be H and then O, like this. Okay, yeah, just want to make sure. So each of these have a subscript of 1. And so our base formula is going to be H1O1 or just HO. Again, if one of these numbers was like a 2, like this, if this divided out to 2, then our formula would be H2O, okay? But because they were both 1, again, it's going to be H1O1 or HO. That's the empirical formula. For the chemical formula, we need to find that part. So let's just kind of do it right here. It said that the molar mass of the compound was 34.0146. That is the chemical formula. They will always give that to you. You never have to find that on your own. Now we're going to compare that to the molar mass of the empirical formula. So to find the molar mass of the empirical formula, we need to add up and find the molar mass. So remember that H weighs 1 gram per mole and oxygen weighs 16 grams per mole. So 1 plus 16, that's going to be 17 as our molar mass for HO, okay? So now you need to divide the chemical by the empirical formula. So 34.0146 divided by 17, I get 2.000, like really close to 2. So when we divide those two, I get the number 2. That means that the chemical formula is twice as big. It's twice as big, 17 to 34. So if it's twice as big, it's scaled up by some number. We need to multiply the subscripts by 2. So our formula for the chemical formula will be H2O2 because it's just H1O1 multiplied by 2. So we multiplied it by 2 because we did the chemical molar mass divided by the empirical molar mass, and we got the number 2. That tells you how much to multiply it. And so these were the 2 problems that they worked in your lesson. If you have any questions or want to work through some more practice, please join my classroom and I'm happy to help you out.